Hey folks, hope you're all doing good and starting to finally enjoy the spring. I definitely am, but in March I had quite a bit of fun. Kind of long story short, I have about 2 centimeters of titanium in my neck, about this level. And now that I'm part titanium, I feel safe to talk about Rust. Today I want to talk about async Rust in particular, and also futures, streams, Tokio, and also sprinkle a little bit of benchmarking on top of that. So the plan for today is to implement a kind of toy clone of do command line application which calculates disk usage, and do it in 3 different ways. Option 1 is to use just regular blocking APIs from standard library. Option 2 is to kind of just straight convert it to async in a straightforward way. And option 3 would be to use some of the more advanced stuff from FuturesUnordered to kind of extract more parallelism out of this async code, and then just run benchmarks and see how it goes. So that's the plan, and let's just dive into the editor right away and see how it goes. Okay, so this is just an empty application created by Cargo New, and let's just make sure that everything just works. Let's run. Oops. Okay, everything looks good. So what we are going to do now is, first let's define just the command line interface for this application. And for this we are going to use clap crate, and in particular the version 3.00 beta 2. So let's go to cargo toml and just add this dependency on clap. So 3.00 beta 2. Okay. Then let's go back to the main and just define the struct. So this is going to be struct opts, and basically today I just want to implement just a subset of do's functionality, in particular just the summarization and the output in a human readable format. So first we need define the options, and the first one is the directory that we are going to start with, and here we can actually define it as an option of buff, where none would mean that we just use current directory as a default. Okay, so that's one. Then let's define the human readable and summarize. Cool. Now let's import what's gonna be. It's gonna be it's just the clap, and maybe also a couple more things, but let's see how it goes. So we also have create version and create authors macros, so let's use them. And here we just derive clap. Okay, good. Now let's make sure that this has the version that we need. Okay. And then let's see if this actually runs. Wow. What? That's weird. Let's try again. Nope. All right. How about now? Okay, so this is better. So I guess we just need to define these bool arguments as like optional flags. So that's what we're gonna do now. So this is gonna be clap, and we need both short and long, and kind of the same stuff here. Let's try to run again. Great. All right. How about now? Okay, good. So let's see if we get the help that we want. No, that's because we haven't plugged the CLI into the main function. So that's what we are going to do now. Basically, we need to add the following thing here. Is it parse? Probably. All right, yeah, so now we have like a very basic CLI for this rdu application. We can actually add like the doc comments on the struct fields, and this will produce a nicer output in the help. So let's document the command line options. So this is going to be a directory to start from. And let's say that by default, this is current directory. Do we need any documentation for these two options? Probably not. Well, anyhow, let's do it. So and then summarize will be whatever. Okay, so now if we just run again, we see that we have a very nice CLI interface in like 2 minutes. Very good. And now I think we can just continue with the actual implementation of the procedure to calculate the disk usage. Okay, let's do it. So sort of let's define this function, and let's call it calc space usage, and it will take path as an input and just produce let's say a result, like an IO of result of U64, and we'll probably need to import the IO and also import path. Okay, so far so good. Now let's just kind of quickly outline the main idea of how to implement this function. So what we can do, we can kind of just sequentially iterate over the content of the directory, and like if it's a file, we just add it to the counter, and if it's a directory, we sort of add it to the queue to process by the same function again. So that's quite straightforward. Let's have a vector that will initially have only path, and let's have the counter that's 0 by default. Now we return at the end again like an OK of size. So this should compile, and this is just a step. So let's integrate it into the main function and just test the whole thing end to end. So here we have the start dir as like notes dir. Okay, and probably we need like unwrap. What's going on? Okay, what type is this? Okay, for some reason it doesn't understand, Rust Analyzer doesn't understand what's going on, but I assume that ops.dir should be option path buff as we defined it. So let's have a start dir defined as ops dir wrap or else. And here we have so here we can use the current dir from the environment. Okay, and doesn't like it. Right, yeah, so we cannot use the question mark inside the lambda. So okay, let's do it like this instead. So if it's some dir, then we just return dir. Okay, that's good. If it's none, then we use the hopefully this should work. Right, so we also need to annotate main as returning a result of unit. And here, this is the tricky part. So we can probably have not just the IO result or like an IO error as an error type, but probably some other error types as well. So we are going to use the kind of catch-all error type here, which is a box of DIN error. Like in real project, I would probably use just anyhow for error management and anyhow result. But here that I guess should be just fine, so that we don't need to have another create as a dependency. Okay, so and here we also need to return an OK of unit. Okay, so far so good. Then we have the usage. And here we just call our function and pass it a start dir. And basically here we just kind of output the results. First the bytes, then the directory. So here we have usage and then start dir. And that's sort of one thing that kind of is a little bit irritating, is that by default, like this doesn't implement display. And this is because I guess like the path can contain non-UTF-8 characters, or be a non-valid UTF-8 string. So instead we have used display. But well, whatever. Once you get used to it, it's not a big deal. All right, so what if we run this again? Let's see how it goes. Okay, so this seems to have worked fine. Exactly as expected. Cool, so let's get back to the calc space usage function. So as I said, the main idea is just we iterate over paths and just do a very straightforward calculation. So let's do this. Well, we have a path in our paths. what we're gonna do, we need to fetch metadata for this path. And there is actually two functions inside std.fs. One of them is called metadata, and another one is like this. Yeah. And we could do something like this here. And the problem here is that this function actually follows symlinks. So if there are any symlinks in the directory that we want to calculate, and if these symlinks kind of sort of create a recursion in the directory structure, this will fail. What do does, it just actually doesn't follow symlink unless you ask it to, and this is what we are going to do as well. We're gonna use a different function called symlink metadata. I think the naming is quite unfortunate because kind of when you see the name you think that it's like a metadata for a symlink, while in fact it's metadata about a file without following symlinks. Which is again like feels confusing, but whatever, we have what we have. So given that we have the metadata, we can learn the file type. Okay, and then we just need to check if it's a symlink, if it's a directory, or if it's a file. Cool, let's do this. So if file type is symlink, basically we do nothing. Okay, if file type is a directory, I think we can get back to this a little bit later. And finally, if file type is file, this is sort of where we just learn its size and add it to the counter. Good. So now to the case where we have a directory inside a directory. So what we are going to do instead, we need to get the entries within our folder, and there is a function. Let's actually maybe go back to the browser and just quickly check the documentation. So rust-fs doc, whatever. So here we have a function read_dir, which returns an iterator over the entries within the directory. Let's check its documentation. So as we can see, it's a result of read_dir, where this is just some struct. Let's open this struct. And you know, this is something that really rubs me the wrong way. So read_dir is supposed to be an iterator, yeah, and what I am really interested in is what type of elements this iterator produces. Okay, I don't usually care about the exact struct that implements an iterator. Okay, and when I open the documentation, I don't see anything about the type of elements, at least, you know, from first glance. The declaration is collapsed. Okay, when I open it, there is nothing in here. Then I can scroll to the trait implementation and find impl iterator for read_dir. Then I open this thing, and then I finally see that the result, like the type of the item, is dir entry. So again, like you can get used to it, but it's just a little bit too much really not needed information. Okay. Anyhow, given that we assuming we have this dir entry, we can get path of this dir entry and do whatever we want with this path. But anyhow, let's just go back to the code and proceed with the implementation. So first let's obtain an iterator. Okay. Then this is an iterator, so we can just use a for loop here. And basically what we need to do is to well, let's first unwrap. As we can see, this is actually wait. Okay, so let's first unwrap here. Now this is probably also result. Yeah, so unwrap it again. And finally what we do, we just push this entry into our paths. So it looks like this is actually not gonna work because path gives us an owned path, which is path buff, and we have a vector of just references to path. So let's change this a little bit. Let's actually accept path buff as an input. And then here, okay, let's clone. You know, you quickly learn that when you have a problem with borrow checker and Rust, you just clone and that's it, or you arc or you RC or whatever. But yeah, that's usually the thing. So what's okay, again we have moved data, so let's use reference here. Okay, now should be good. Let's try to run it. Okay, what about do? Well, that's kind of close, I guess, right? Yeah. Okay, so looks like it's actually working. So what we're going to do next is just implement the better output of the size of the directory, basically like a human readable, how many megabytes, gigabytes, terabytes we have. And for this, we are going to use another crate. Let's actually switch to browser and find it here. It's called humansize. Humansize. Yeah, so basically it provides a trait which has the file size, adds the file size method to like Q64, for instance. And that's what we are going to use now. Okay, let's go back. And here it should be, I guess, pretty straightforward. Okay, now this is, okay, we need to unwrap this and just use it here. Well, results differ. I guess this may be because of the different sort of translations, like megabytes, megabits, what is it, like a power of 10, like 2 to the power of 10, whatever. So let's see different options. So we have decimal, binary, and conventional. Let's try binary. What's it gonna be? Oh, same stuff, but just a different notation, whatever. What about decimal? Okay, that's even higher. Let's stick with conventional. Maybe there are different ways to estimate the disk usage. I don't know. Not exactly sure what do uses here, but it. Oh, that's kind of a little bit confusing, to be honest. All right, here's an idea. So maybe this is because of this. Hard links counting multiple times seems plausible. So let's try this out. So it's gonna be like this. Okay, now all right, now we're actually closer. I think that's sort of close enough. So basically the difference is because of the hard links, and to kind of then compare this like do and rdu benchmarkings, sort of apples to apples. Let's just add another flag to the command line interface. It will do nothing, but it will be easier to set up benchmarking for different binaries. So let's, what was it called? Count links minus L. Oh, now let's define some collab options. So short should be L, long will be automatically generated. That's fine. Let's see. Okay, cool. Yeah, that's right. So that's pretty much it. That's the whole implementation. We just have like a straightforward cycle. Other than confusing name, the API is pretty easy to use, so looking good. Now let's see how the performance looks like how the rdu fares against the venerable do. So I actually have a directory set up just for this. As you can see here, I have like a couple projects here. Probably Linux source code is the bigger one. Emacs is also quite big, but anyhow, so to run benchmarks, I am actually gonna be using hyperfine, which is one of this new generation of command line tools built in Rust. So hyperfine is quite cool actually. So if I open help, it kinda you give it a command, and then there are some options, and one great option is this where is it? Yeah, it's this parameter list. So here we can set up different binaries and then just parameterize the command, and it will run all these binaries and then compare results. Very nice. So let's do this. So basically what we're gonna do is run hyperfine. Then we have this parameter list, and actually let me do release build first. Cool. Now to hyperfine again. So here I have target, release rdu, and then here do. And the command itself, I think we actually need to name this like this, maybe, possibly. Let's try, whatever. So here we have an executable, then we have HSL and the directory. Something, no, something's not right here. Okay, so probably no spaces. Hyperfine the shell. Yeah. Okay, this looks better. All right, so what we see here is that well, do works faster by about 40% faster. And actually this is quite good for the implementation that like takes how many, like 20 lines of code, pretty straightforward. I think that's a good result. So now with this like a blocking standard implementation, we're done with it. Let's kind of do the let's rewrite it and make it async in a most straightforward way. So what we are going to do for this is we are going to add Tokyo as a dependency. So version 1 and full set of features. Okay, and what I think we will do is let's actually create a new folder here and also a new file, librs. Then let's move the CLI definition into the library part of the crate. And there's things here as well. Okay. Oops, that's a little bit too much. Now let's go back, remove this. Actually, let me just move it into bin and rename. This is gonna be rdu-sync. All right, now we need to import rdu opts, but those are not public. Let's make them public. Okay. So let's do cargo clean. So if everything is fine, we should have rdu-sync binary under target debug. Okay, yep, that's good. All good. So now let's create a new file here. actually, let me probably just copy paste what we have. Where's the, come on. Cool. And I will also rename it to async. And here we will have just sequential processing. So no sort of parallelism, concurrency, whatever. Just a very straightforward translation from sync to async APIs. So Rust Analyzer is not happy. Why? Okay, so we already have Tokio as a dependency added to the project. So, and Tokio actually, let me maybe open the documentation here. So Tokio actually has a file system module, and it sort of mimics the std.fs module very closely, but kind of provides an async Rust wrapper around the standard functions. So for instance, we have read_dir here, and we have symlink metadata. So if we have a look, we see that it's actually an async function. So this is the same sort of read_dir, but from Tokio, and it again like provides some like async API. But other than that, it's like very, very close. So what we can do instead is just to replace std.fs with tokio.fs. And just insert async await where needed. Okay, like a super straightforward translation of the synchronous code to kind of use async APIs. So here, tokio.fs symlink metadata is an async function, so we need to wait on it. This is also needs to be waited on. Now, yeah, so this function needs to be made async. Then we need to wait here. All right, then main needs to be annotated as async. However, main function cannot be async in Rust. So instead, we just need to use macro from Tokio, which will do some magic. It will basically create a sync main, which sets up the Tokio runtime and just calls our async main function. And finally, there is this final piece here where we have entries, which is a read_dir, but from Tokio this time. And in with std.fs, read_dir was an iterator. But here, like in async Rust, we don't have asynchronous iterators. So we cannot use the same like for loop to work with this structure. So we need to massage code a little bit just to make it work in the asynchronous setting. So there is a method called next entry, which is just an async fun that returns like a result of option of dir entry. So what we need to do, we need to await on it and then replace this for loop with a while loop. And now we don't need this. And finally, we need to make entries mutable. And this seems to be it. No more errors. So let's try to run it and see if it works. Okay, how about sync? And finally, all right, that's close enough. So let's build the release versions of binaries. And while we're doing this, let's just take one more look at the code here. And what we have is like the differences between the regular blocking standard APIs version of rdu and the async version of rdu. Like they're really minor. So basically we have a couple more async here, a couple more awaits, and the while loop instead of a for loop. But that's pretty much it. It's again like a very straightforward translation. And I guess it would not be fair to expect better performance from this, just because we are still doing the same sequential processing of files and folders, but now with some overhead from async. Like we now have this these structures, like kind of futures that yield control back to the Tokio runtime, context switches, and all this. So it would be fair to expect somewhat worse performance compared to the sync version, but I guess we can just run hyperfine again and see how it fares. Is it gonna be like 2x, 3x worse, maybe closer actually? So let's just run it and see. So we have the hyperfine, the shell. Let's have do first, then and finally the async-seq version. Here we need a directory as well. Okay. Looks good. So let's run the benchmarks. Du's performance is the same. rdu-sync is also the same. All right, this is taking a while. $19.9 seconds. What is it, like 70, 80 times slower? All right. I mean, I did expect like 2x, 3x difference, but definitely not 70x. That's quite a tax, quite an async tax. All right, I just need to process this a little bit, and while it's finishing, let's maybe just bootstrap another version of like an async implementation. So let's copy and paste and rename it to async-par, because basically the idea would be to try to do as many things as we can in parallel or concurrently, and try to get back this extra performance while doing many things in parallel. Maybe we'll burn more CPU cycles than the in the sync version, but hopefully we can go faster. So let's see. Basically, here we have several await points in a loop. So this is the first await point where we fetch metadata for a file. then there's the second await point where we kind of create this asynchronous listing of directory entries, and finally here we sort of kind of walk over this asynchronous iterator, just pushing these paths to the list process. So I think it would be fair to try to do these things concurrently, and also these things concurrently. And for this, I think it would be good to actually start with look at some documentation first. So let's switch to the browser, and okay, let me open a new tab and open the Futures crate. So Futures has some like helper functions to work with Futures and streams, which is like an asynchronous version of an iterator. And one thing that it has, if we actually go to the streams section, what it has is this like a FuturesUnordered struct. And what this struct does, it kind of allows you to pull many things concurrently. So basically we can we can push as many things to this FuturesUnordered, as many futures, and then they will all be waited on, and the first one which is ready will be given to us, so we can repeat it, and this will basically allow us to wait on many things in parallel. So let's actually do this. So what we can do is probably okay, so let's call it a meta queue, and this will be FuturesUnordered. Oops, forgot to switch to the editor. New. All right, so we need to add this to the dependency. Sure. Wait, that's the wrong binary. Let's go to async-par. So we actually don't need this, but we need to push this first kind of future into the meta queue. So let's create a function here. So it will take path and return an IO result of metadata. Okay, and here we will have the this part basically. So now what we can do is we can meta queue, push, and here we have meta for path. Okay. So now we need to change this thing. Next. So this gives us well, now this is where it is it starts getting tricky. So it says it returns a next, and this is again the same thing. Like I am given the concrete structure that implements something, and this is not what I'm interested in, right? So maybe there's some whatever. So let's wait and see what we have as a result. This is like result metadata error. So maybe we could just do one more thing here and use futures. Is it like stream, try stream next. And this will give us the try next function that we can await on like this. And now, yeah, so path is just metadata. Cool. But here it's actually meta. Okay, so here's another problem. We not only need metadata, but we also need a path so that we can, if it's a directory, read from it. Okay, so let's change it. Let's change this function to return the path that was given. Okay. Now, basically what we have here, we have again like some directory entry and we have a path, and here we need to kind of push this thing into the meta queue, I think. So let's see. Yeah, so this is actually getting quite tricky. Takes quite a bit more brain cycles and focus to kind of understand what to do. So let's see, we push into the meta queue, and here we have meta for path, and this is going to be like entry path. Okay, so this seems to compile now. Let's actually, okay, so the results are actually done. So what we have here is 85 times slower than do, and what is it, like 85 by 1.4. So yeah, so this is like 60 times slower than the sync version. Oh my god. Anyhow, so let's run the parallel version. This keeps just keeps growing and growing. All right, so how about, okay, so still good. Now how do we sort of parallelize this thing, kind of make it also run concurrently with all the other stuff. So let's see. Let's maybe switch to the documentation and open. So basically, let's say we have this asynchronous iterator. I guess we can kind of turn it to stream. So let's see, Tokio stream, Tokio stream. Okay. So here we have wrappers, and I guess this is what we need. Wrapper on Tokio, redir that implements stream. Cool, so we can use this. Now let's say we have this stream. What we can do with this stream? So let's see futures. Let's see what we can do on the stream. Okay. This actually looks good. So basically we have a stream, and then we call into future on this stream. And this feature, when resolved, will give us the next dir entry and the tail of the stream, which we can call into future again on. And sort of this will allow us to get these next entries in a particular directory in a non-blocking concurrent way. And then we can have probably like two queues, two futures unordered, one for the meta, one for the entry, and then we can wait on them in parallel. So there is actually another thing in futures. Let me open this. This is a macro called, this is a macro called select, and this allows us to poll multiple futures or streams simultaneously. And then we can sort of poll this like meta queue and a entry queue, and whichever resolves first, we process it and sort of minimize the amount of time we actually wait on something while not doing something productive. So let's try to work our way out of this. Cool. So let's create another queue. So it will be empty at the beginning. Then when we get this like read dir thingy, we need to convert it into a stream. So we need to add like the Tokio stream library into our depths list. All right. Then we just push it into I think it was into future. All right, so what was it, like read dir stream? then we have entries stream into future. Okay, so this looks good. Let's just command this for now. And now this is a this is the tricky part. We kind of need to wait on both things, and here we actually need to use, so let's try to use like a loop instead of a while loop, and here we need to use select macro. Bam. So first we try to wait on the meta queue, and here there is this handy function called select next sum. Actually, let me just quickly get the documentation for this function. So I will So this is more or less implemented specifically for use inside select macro. Yeah, so like this. Let's go back to the editor. So looks like Rust analyzer is just doesn't understand what's going on. All right, whatever. So I guess we can just kind of move this whole thing here. Okay, so let's go back. This is really tricky. So we have select next sum. What is this? Exactly. So it's a future. Nice. So it's st item. All right, so my bad that this is actually a result of path buff metadata. So let's kind of copy this thing inside this thing, and this is actually so. No, I didn't expect this. So Rust FMT doesn't work with selects nicely or at all. So yeah, one more. All right, so here we have the path meta. Hopefully it will work. Now we don't need the while loop here. Okay, let's do that. So that's one branch. Now we need another branch. And this is like where the entry queue is ready. And here, so entry queue will give us a tuple of the dir entry and the tail of the stream. So let's see, entry tail. And here, let's just take this thing, copy it here. So I guess with tail it's pretty easy. We just kind of turn it into future and push into entry queue again. So let's do this. Entry queue push. Well, it's very frustrating that Rust Analyzer is just completely lost here, man. Okay, so this is done, and now we have the entry, and so we just need to kind of push it into the meta queue, or not the entry itself, but rather like the future that will return metadata and path buff. So come on. What's wrong? Okay. So macros seems to be like the answer for everything in Rust. And they do help with the ergonomics sometimes, but sometimes it's just quite clunky. They're quite clunky to work with. Okay, go back, meta queue, push. Okay, so entry seems to be option of result. And I guess when it's none, the tail should be empty, so we can kind of just skip adding it into the entry queue again. So let's do like this. How about now? All right, but yeah, that's quite interesting. So Rust C tells that like this instruction is unreachable, and that's fair. Basically, we have this loop and we don't have any way of breaking out of this loop here. So there's actually like a special thing in this select macro, like a special branch, which is called complete, and these branch is taken when actually like all the streams are done, like are finished. So here we just call break, and that's it. Let's try again. Okay, that's cool. So we don't need try stream next. All right, so let's try to run it. Nice! So this actually works. Okay. Man, the size of this directory just keeps growing. So, okay, fine. I guess we should be good now. So if we take one more look at this implementation, so this is actually quite a bit more complex than what we had before. I guess like first, it's just not great that we have this like big chunk of code in red squigglies in the in the IDE, while it is actually a valid code that compiles and sort of works fine. This is not cool. Also, the formatting doesn't work within select macro, and I just like the types are really complex, and it's the like Rust Analyzer doesn't help much, like in with the inferred types and just understanding what's going on. Yeah, so this is much more complex, but hopefully this complexity will help us to achieve much better performance than the sequential version. So let's try this out. I guess we could just build the release version. And before we go into the benchmarks, there's actually one problem with this implementation. So it tries to do this much like stuff concurrently, that if the directory is big enough, we can just run out of the file descriptors. Sort of, there's like the default limit of 1024 open files, and it is possible that this will kind of consume much more, and with this will result in failure. So this can be alleviated, right? So we can probably have some I don't know, like a blocking queue in between that will provide some form of back pressure, and will keep the number of open files at some okay level. But I don't think that we want to complicate this even more. So hopefully it will work. If not, I will just raise the U limit, and yeah, that should help anyway. So let's go back. Let's run hyperfine. So let me add rdu-async-par. Oh, come on. And let's see. Bam. Da-da-da-da. Well, I mean, this is indeed faster. It's like, it's not 20 seconds, but 8. So it's like 2.6 times faster. But still, it's just abysmally slow compared to this simple version. And the code is so much more complex or even complicated. So yeah, I guess let's just make it run and see like the final results in the nice table. But probably one thing that's gonna be interesting to do is to try to run this like the same benchmark on some, let's say, other operating systems. So here I am actually using WSL2, which is kind of the real Linux, but on top of the Windows hypervisor. And since IO subsystems are implemented differently between Windows and Linux, I do expect to have different results between like native Windows and WSL2. Whether there will be differences between WSL2 and native Linux, we will see. But I guess let me just quickly boot into native Linux and then into like do the same set of benchmarks for Windows and present it to you through the magic of editing. All right, so let's start with native Linux results. Here actually, I mean, it is quite different. It is quite different for sure. So it is not like 60 times slower or 80 times slower than do. It is like 4 and 12 times. And the parallel version is just kind of 4 times slower than do. But sort of, it's still a little bit too much, to be honest. I mean, this code is quite, I mean, there was effort put into this code. And this is like 12 times slower than do and like 10 times slower than the the sync version, this still feels a little bit too extreme. So what I also did, so these are results with the warm disk cache. I also tried to do the same, run the same set of benchmarks with the cold disk cache, and actually it is also quite different. So in this case, async-par was quite a bit faster than like do and rdu-sync and async-seq. So this makes sense actually, that the parallel version works faster with the cold disk cache. But still it is just 2 times faster, which is not that good. And I'm not saying that it is like Rust to blame. It's probably the like me to blame and my implementation to blame for the slowness. But let's maybe like take a look at the Windows results as well. So here on Windows there is no do, so it's like a limited set of benchmarks. I also don't know how to flush like clear disk caches, so it's just warm disk cache. And in this case, the parallel version just a little bit faster than the sync version, and quite a bit faster, like the same 3 times faster than the async-seq version. So here are my takeaways. First, I had this implicit assumption that async is better than sync all the time, period. So in my projects, I sort of reached out to async Rust and async APIs by default. And I just assume that kind of blocking APIs suck, and I just don't need to even try to use them. And the reality proved to be much more nuanced than this. As we can see, this like 20 lines of code blocking implementation just blows out of the water pretty much like both async implementations. Right, the async-par outperforms the blocking implementation only with the cold disk cache. So I guess for me personally, the takeaway is async by default may be the wrong default, at least now, and that there are probably quite a few workloads that can actually be faster with when you just use blocking APIs, and the code will be clearer. And probably one thing that it would be interesting to note is that, so with the async-seq version, it was easy to see that we should not expect a better performance out of this, right? Because we still have the same processing, sequential processing. So all we will have is the overhead from using async. But I would argue that in a larger system, it may actually be quite easy to kind of fall into this trap and implement the similar sort of naive async version of a particular functionality. And if this thing turns out to be on the critical path of your application, it can negatively impact performance. And as we can see, the impact can be like really huge. So I guess this kind of ties to the next point, and this is the ergonomics of async Rust. And again, currently it seems to be hit or miss for me personally. It's like, sometimes everything, just flows and the code is easy to write and easy to read. It's just great. But when you try to do something more complex, then it gets ugly pretty quickly. Like you lose IDE support, types get much more complicated. You need to use the this macros that may be hard to kind of understand. So also you probably have to fight the borrow checker quite a bit more, because you should restructure your system to make sure that you have to own the objects that you pass between the async tasks and so on and so forth. So this adds quite a bit more complexity. And let's say something like streams are not very ergonomic in async Rust right now. I hope it will get better soon, but for now, yeah, there is this downside, price we have to pay for using async Rust in somewhat more complex scenarios. And I guess the final thing is performance, and the fact that it varies so wildly across different operating systems, and even kind of the same operating system but with a kind of different setup, right? So on Windows it's kind of one picture. On native Linux it's completely different, but let's say WSL2, which is the same native Linux but on top of a hypervisor, it's again even more extreme. The difference in performance between the blocking and the naive async version is like 60x. This is just so extreme and so surprising for me personally. And it's really hard to kind of predict what kind of performance you will get unless you actually do benchmarking on all the major operating systems, which is, I mean, that takes quite a lot of effort. But I guess if you care, it needs to be somehow incorporated into the working process. All right, let's wrap this up. All the code and benchmarks and the description of the setup will be on my GitHub. The link is in the description to the video. I hope it was helpful. If I did something stupid, let me know in the comments down below. If there are some tips and tricks that you would like to share, same. Otherwise, thanks for watching. Have a good one, and see you later. Peace.